state hurts everyone. Stage is yours.
Thank you. I'm just going to put on a timer for myself. So, hello, my name is Sverrir Thorgeirsson, and I am a PhD student from ETH Zurich, Switzerland. And I'm here to present this essay that we call "The Hidden Program State Hurts Everyone." So, first off, before I go into the main point that we have in our essay, I just want to show you some pictures of non-software developers working with computers. So, in this case, we have an air traffic controller who is looking at radar and communications information on a computer. We have a meteorologist analyzing weather data, a physician looking at patient data, and finally a seismologist working with earthquake data. So, of course, this looks pretty weird because this is not how these photos actually looked like when I found them. So this is what it actually looks like when people work with these technologies, at least according to the news reports where I found these images. So my question is, if this is how it works for so many different professionals, not limited to just these four professions, why is it that software developers work so extremely differently? So, in contrast to how they do it and how we do it, we work with static representations of text, kind of like this, while they work with dynamic representations. And it's not like that we are able to take a look at this and understand immediately what this means. We construct our own mental representations of the code to understand the state of the thing that we're trying to model or to comprehend. So in many cases, we think that these textual representations just add a layer of complexity to the way we do things. So when I was preparing these slides, I was asked by one of my colleagues, well, why do you have to make it a guy from the Matrix? Like, this looks just really cool. Like, I want to be this guy. Like, these movies are impressive. Like, we think it's cool because, I mean, we don't understand what's going on. We see like these, kind of like what Fellini was talking about in her presentation on Wednesday. Like, we think that when something is difficult, when something is totally incomprehensible, that means, wow, this is something I want to do. Like, this is something I want to aim for. This is something I want to make a career out of. When things are easy, like if the Matrix was built in scratch or a block-based language, I don't think this would ever have been popular. Like, there would not have been any sequels. So, and this leads me to the next question, like, why does this even matter? Like, if computer programmers are so happy with the tools that we have, well, does it impact them negatively? And we think it does. Like, we think that these complex representations that software developers work with, that they harm their performance. And to moderate this belief, I would like to take an example from chess. So I have this book that I got when I was a child called Cross the Board with examples of chessboard problems. This is not quite the same as chess problems. These are problems that are based on maybe simpler representations of chessboards with different types of pieces. So this here is the oldest chessboard puzzle in the world. And the goal is to find a sequence of legal moves for the knights so that they swap positions. So this is something that is relatively difficult to do. Not particularly challenging. So for those who are not familiar with chess, a legal move on this 3x3 board would be that the knight could move to a non-adjacent square of the opposite color. So we could, if we are allowed to see the state, and if we are allowed to manipulate the knights, we can find a solution after some trial and error eventually, like kind of like what you're doing here. This is a very nice way to actually work with the problem. It's called direct manipulation. But if we were a computer programmer, this is more like how we would do it. And this is just a terrible way to do things. You see, we don't see how the state updates after every sequence of moves that we have made. Like, it takes a while. We can make errors, and like it won't run. And we have a hard time understanding like what the error messages even mean. So I think that this example is a very good illustration of the problem that we are experiencing, and like how much nicer it is to have an ever visible program state for whatever task we are doing. And moreover, the point with this particular example is that not only does the state representation matter a lot, but that we also have a good state representation. So you may have noticed that, like for this chessboard problem, the legal movements for the knights can be modeled as a graph, like you can see here on the left, which can be untangled to give a better state representation. So when you do it like this, the problem is a lot easier to solve. So on the left, it's trivial to see like how we can actually swap the positions of the knights. So you see like what we're doing on the left has a matching move on a state representation of the right. So this is very easy. So I want to take this further and try to understand better what examples like these ones and others can tell us about how we should design good programming environments. And what serious or professional chess players like to do, in addition to playing games, is to analyze their games, and they use software to try to do that. They have engine evaluations telling them how they could have played better, and like they try to look at games and understand how their opponents have played in the past to get a feeling of what they might encounter in their actual games. So a system like this looks in many ways similar to an IDE for a computer programmer. But maybe the biggest exception is that we have this state representation of the problem that we're trying to solve on the left side. And that comes with some useful features like some visual scaffolding. We can see like what was the last move that the player made. We can see visually what would be the suggested move from a computer in a position. We see like a history of the moves that have been played in a game so far, and we can explore variants that we can easily step into and expand and collapse. We can see a history of games that have reached this position and the success rate that players have experienced in these particular games, and so forth. This is also similar to how professional creatives work with image editing. We have like a state representation of the image that we're trying to build. We have here on the left, we have like clickable actions that we can use to manipulate the state, and we can see this when we use it. We can see how it affects the state immediately. We don't need to like write this and wait for it to compile. We can skip this edit compile cycle altogether. And what I have been trying to build together with my collaborators at ETH over the course of my PhD is a language for programming that resembles this in some ways. So here at Onward, Essays22. I was here with my talented collaborator, Theo Waitman, who we submitted a paper on this programming language Algot that has some resemblance to like this chess software that I was showing you and the GIMP image editor that I was showing you before. So we have the program state, which is always visible here in the center of the screen. We have a list of actions that we can use to change certain features of the state, and we will see how this affects it immediately. And we can use this program state to create functions. We can do programming on this. We can do quite a lot with it, actually. Like, I'm going to show you a video of how a recent version of the system could be used to create a function that computes the dot product of two linked lists. So right now here we see that I have created a function which we call dot product, which takes 3 input nodes, which will be used when you call a function in the future. These are the nodes A, B, and C. We define some example values for these nodes. So we can see when we do actions on the inputs, how their values change. Not so that these examples have to be the values of the input, but just so that we can get a better feeling for how the things that we're doing affect the program as we are writing it in a live way. So here we create another temporary function called addProduct, which we can use for the function, which will take 3 inputs, take the product of the first 2 nodes, add it to the third input node. We create some example values. We create a temporary new node to store the product of A and B, just like this. You see 2 times 3 is 6, so these example values are helpful to tell us that we actually succeeded in what we are trying to do. We add this value to the node that had the value 1, so 1 plus 6 is 7. We can use the program editor to see, like, to step through this function. This is a new feature. And then we can use this helper function here in this dot product operation. So you see now the value is 8, and we call the function that we're defining recursively, again, on the child nodes of A and B. And this is all we needed to do to create a dot product that works on 2 linked lists and the third input, C. So if we then try calling this on some alternative versions of the input, we can step through and make sure that the program actually worked. So, and we can step into like the function calls. We can see that this works in a general case. So we create 3 new nodes. As you see, Algot is entirely graph-based. The program state is just going to be one big graph. We create some example values. And call a function we just defined on the parents 3 and 1 and the node 0. And we should see the value 3 plus 2 times 6, 15. So we know that this works. So we did all of this without writing any code. And more importantly, we were able to see how the program state changed throughout the entire, not execution of the program, but through the definition of it, which I think matches nicely with how we can do other types of creative work, like I was showing you before. So some changes that we have made since we presented this paper in 2022 is that now we have a proper program editor, which is what you see here on the right, that we can actually use to step through the program. We have support for example-based programming that allows us to see on a more granular level, like how the input is changing throughout the definition. We have support for custom queries. We can do branching like we did before, but in a more detailed level than we made possible. And we have made some simplifications that mean that we no longer have like a clear distinction between the parts of the system when you are defining an input to a function, when you are asking questions about it, and when you're doing actions like calling existing operations, which seems to work rather nicely, at least for the context where I tried this. So far, where we have been experimenting with this is in computer science education. So this is where it seems to be most effective. And the reason, or well, there are many reasons why we have worked with education as a starting point. One point is that this allows us to gradually build the features of the system, that we can start with more simple things that are nevertheless important to students to learn. It's also something we wish to do because I think computer science education is very important, and that more computer scientists should care about it. And also because of these attitudes that we were talking about, that I was talking about in the beginning of this talk, that I think that many developers don't necessarily see the value in working with a system that radically changes how they do computer programming. In a way, maybe that can sometimes devalue their expertise, or make it more accessible to others, which is not necessarily what people always want. So this way we can try to not only present a tool that is effective for hopefully a lot of people, but that we can also change the attitudes that go along with it. So another question that I get frequently when I show this tool to people is, why do we need something like this? Why aren't the existing tools that we see so many papers right now on in CS education venues, why aren't they sufficient? And this is just because of the problem that I was talking about earlier. We think that, for example, block-based programming does nothing to address the opaqueness of code, and neither do large language models. So I want to show you that, and I think this is very important, to validate whether this actually works. We do a lot of user studies, and this is something that is appreciated in CS education venues, and I would definitely like to see more of in general when it comes to new technologies. We do user studies with students of every age group. We did, for example, a study on secondary school students with an average age of 14, where we showed them Algot, and we asked them to compute some recursion-based tasks, like, for example, to take a tree input and to compute what would be the depth of every node in a tree. And then we gave them a similar environment in Scratch with the same tasks, using the so-called make-a-block feature that also supports recursion for Scratch. And then we gave them a post-test, which was based on a validated instrument for measuring understanding of recursion, the basic recursion constant inventory. And we saw that in this measurement that students both performed a lot better when they were working with our system Algot, which we attribute to them being able to work directly and see the program state at all times. And also they performed a lot, they had a lot higher learning outcomes, probably partially due to chance, but nevertheless this is a consistent trend that we see. So Cohen's d, that means the difference between the two means of the populations that we tested divided by the pooled standard deviation. So, and we did another study with undergraduates when we compared Algot against Python, this time with simple programs that did not require recursion. We measured their cognitive load. We used eye tracking and galvanic skin response to understand if they thought the tasks were challenging, and surveys on top of that to see like which self-reported cognitive load levels students were reporting. And again, we saw much stronger performance in Algot and a lower cognitive load level also in our system. We did a study on program comprehension when we showed the students existing programs in Python and Algot and measured their performance on some questions that we asked them about the programs, like to measure how well they understood conceptually and mechanically what the programs were supposed to do. Again, seeing a strong performance improvement and a slightly, but not very meaningfully, higher enjoyment. And lastly, this was a study I just presented now in August. I did another study with undergraduates where we actually measured their cognitive load with an EEG, like these headsets that you can see here in this small image on the right side, to measure, to get a more objective understanding of the cognitive load levels. We can, it's possible, according to the literature, to convert the surface level electricity levels from a scalp into different frequency bands that whose strength corresponds to different levels of cognitive load according to some of the bands. So we looked at the theta and alpha bands coming from this equipment to understand if their cognitive load level was different. And this time we used more complex tasks. We used trees and linked lists. And again, the control environment Python to see how students compared. Again, seeing a strong performance improvement, but this time not a meaningful difference in cognitive load, according to neither the EEG equipment or the surveys. But for all of the studies, we are comparing our language against something that students are already familiar with, both Python and Scratch, further strengthening the results. So I think we see a rather consistent picture when seeing if this language actually is effective. So what we see here is that for students, for CS education, this seems to work, at least in the context of the studies that we tested. I don't think this is has to be like the ultimate solution to how students learn programming, but I think it is at least a good start, and it validates some of the thinking that we have been having about how we can make more effective programming environments. But what we have been thinking also about over the last years is this something that we can actually extend beyond CS education? Is this something that can actually work for professional developers? And we are at least hoping that this can eventually reach that level. One question that you might ask when you see how Algot works, like in the example I showed you, is how does this work when we have an enormous program state? Typically, we're not trying to do such simple activities like trying to compute the dot product of two lists. We are maybe working with billions of variables or data sets that contains, or spreadsheets that contains millions of lines. And the system that I showed you is doesn't work in the current form to deal with something like that. But an idea that we have is that we can hopefully try to abstract this a little bit so that nodes can represent a more complex structure, which can in turn contain elements that contain a more complex structure in turn. Something like this, so that we could have a node that represents, for example, a list of guests, and so that each guest represents some more complex structure, like what we see here on the right. And another question that we get when we talk about how we could try to extend Algot to work for professionals is, well, since Algot is graph-based, how would this work for some different types of data? Like, can this actually, is this scalable for some existing data that takes some other forms, like tables, for example? And my opinion is that, well, maybe not. Maybe Algot is, it's possible that this is not going to be the best tool for the job, but my opinion is still that the computational paradigm that I was showing, and like this idea that working with a program state, like you would when you're working with doing something creative, like working with, like when you're working with Photoshop, or like when you're working with analyzing weather data, or like whatever examples that I was showing you before. We can extend these ideas onto all kinds of different programming environments that have different data representations. So this system that I'm showing right now, maybe this could be a start of something. So that is the main takeaway that I have for this paper. So that's all I want to say for now. Thank you.
Thank you for the talk. There's time for questions. Maybe I start with a quick one so that everybody can line up. Do you have an idea how you can transition the early CS education following these approaches, maybe to learn about, I don't know, computation, or some abstract thingy, to another kind of programming activity? Have you thought about, well, did you call it serious? I don't know if you called it serious programming, but
I could.
Have you thought about how to go from there if you have the chance to get the early CS students?
Do you mean how we could adapt the empirical methodology?
You make up a goal, what they should learn. So like, I don't know, if you prepare them with Java and OO, or what would be an interesting learning goal?
So this is a question we keep asking ourselves, actually. How do we do similar studies with professionals? And it's hard. I think we could not show a completely new tool like this to a professional developer and ask him to do the same tasks like we've been doing in our existing studies. We could not ask him to do the same tasks in Algot and React or Java or whatever, because it would obviously be too imbalanced. I don't think our system would fare really well. And also we have an issue with attitudes. Like I think many people just don't see programming as something that needs fixing. So I'm not optimistic that we could adapt this methodology so readily, but something that would maybe be worth considering is to see like how this could work for non-experts, like citizen developers, like people who are trying to do meaningful tasks with low-code or no-code tools, or even large language models, and see if this is something that, well, if it doesn't necessarily lead to like performance gains, at least improves their learning in some way of computer science. I'm optimistic that maybe that could be possible.
You're referring to the initial examples, right? Air traffic control and so on.
Yes.
Also, okay. Thank you. Let's have a next question.
Sorry. I tried out the Algot tool, and it was maybe the most satisfying to use of any visual programming environment I've ever tried.
Thank you.
At some point, I tried to make things that were a little bit more complex, and what I liked was the little sidebar area with the list of instructions and so on. So what I'm wondering is whether in any of your experiments you found how much people used that, and did they at any point start shifting or do different operations in the graph view versus in moving things around in the sidebar and so on?
I'm sorry.
Can you repeat the question, maybe?
Sorry,
you go please closer to the microphone.
Sorry. There's a little list in the sidebar of instructions of basically based on the things that you did, the manipulations you made of the graph. Yeah? The little the tracing area on the side, which you can...
I'm not sure if I heard you or understood you properly. So are you asking me if I observed some difference in when people start to do more complex tasks, if they prefer to use the...
yes, but essentially yes. Is there a pattern of behavior when they start to look at that trace more often or less?
This is not something that we have observed in any empirical studies, like difference in behavior. Of course, as they start to do more complex tasks, they also grow more competent at using the system at the same time. So it's hard to that's a confounding variable, I would say. But what we have observed, like with the new text editor that we have, this supports debugging. So once you start to do something that is more complex, you start to make more mistakes too. And that's one pattern that we see, at least, that people start to interact more with this small history bar that we showed here on the left in the application, that maybe they start to do more activities like dragging and dropping or rearranging existing operations to correct mistakes or like try to achieve something that they couldn't do in the first attempt. So.
I guess I'm wondering about the assumption here that even if you can visualize the state, whether it's graph or otherwise, whether that's always useful in order to do incremental programming. So I used to do like spacecraft simulations back in the day. And there's a very natural visualization. A lot of the new tools have that, where you have a little image of the spacecraft, and you can see it orbiting, and you can see it moving. But I'm not programming to get it to move a certain way. I'm programming the equations of motion and putting it into an environment, so it'll tell me how it's moving, so I can see if the design is right. So it doesn't really help me to be programming and watching it move, because I'm not sure if it's moving correctly or not. And I'd say there's a lot of situations like that, avionics, even banking, which has to conform to a lot of regulations and whatnot, where you can't just incrementally create based on, even if you have a very good representation of the state, because you don't know if it's right or not, because having it be right or not is usually something you have to look at over a lot of data and do a lot of tests to determine. And I have to, either implement the equations of motion of physics or implement the banking regulations or whatnot. Does that fit in there, or is there just a restricted range when this
I mean, I think
approach
you just
would
might
work?
have a good point here. Like, maybe it's not going to be like the be-all or end-all of computer programming, like this way of thinking. But I guess what I wonder is, does it have to be? Like, maybe it can be helpful for a large number of tasks that we are not currently using this paradigm for right now. We could use this, we have tested this to do more complex applications, and we have not yet hit a roadblock. We have seen like how people can use this to build simple CRUD applications that they would struggle with in textual programming. Maybe eventually we're going to start hitting roadblocks where like we see diminishing gains or that this doesn't work altogether, but I think that's maybe okay.
To see it on more advanced CRUD operations. Also, you mentioned low code and things where you're incrementally adding.
Yep.
If somebody's already built a system, if you could visualize it in order to maintain it and operate on it, I think that would be a really good application also.
Sure, but my opinion is that there's actually surprising how far you can actually get with this. There were things in the beginning that we did not think was going to be possible using this paradigm, but we keep expanding on it and seeing more and more things that we can actually do. So I'm optimistic, I would say.
Push it as far as you can.
Yeah.
Thanks for thought-provoking talk. You asked two questions in your talk. One, whether this can be applied to professional development, and also whether graph-based visualizations are appropriate. So we actually do that in our company. So we're always trying to expose hidden state and create custom views of software. The thing is that we don't know in advance what states are going to be interesting. And as a consequence, it needs to be very cheap to add new views to existing objects of the state that we're exposing. As a consequence, very often we find that very simple views can get you a long way. Just simple tables and lists that dynamically update are very useful. Sometimes we want graph-based visualizations, and we have a nice little engine to do that. That's a bit more work. Or bar charts, or completely ad hoc visualizations, and they're more work. So I don't know, if there's a question there, my question to you is, have you considered the cost of building these views, and also the aspect of that you may need to add new views of hidden state while you're working on an application, instead of doing them all up front?
So thank you. This is a classical problem, I would say, with programming by demonstration systems, like Algot is, like that. Creating custom visualizations is a time-consuming task, and it's not always worth it. But what we are hoping to achieve here is that this is something that is at least somewhat general purpose, like that you could imagine how for a programming task that you could build like customized like visualization of table or like some special data structure that you have for your system, and that this would be difficult. But we are hoping that if you build your entire system this way from the start, then well, maybe this is something that can limit this cost that we're talking about here. So we will see like how far we can get.
Thank you.
Well, maybe one more question. Thinking of I think the comment on simulations and maybe tweaking simulations with this kind of programming approach. And what do you think, as you just said, like building it from the ground up versus just using it where it fits, right? So like a domain-specific configuration language thingy, like, what are your thoughts on that? So it sounded to me like you don't want to give up too early, so it's not just the domain-specific configuration approach where nodes and edges fit well, but maybe to construct more out of it. So I'm curious, why do you go this way? Because on the domain-specific language area, people are like, okay, that's fine. It works perfect for this use case and maybe some more, but we will never try to build, I don't know, an entire operating system, whatever, big. Yeah, so maybe you can share some more thoughts on that. Where, when, how do you push your boundaries? And yeah.
I'm sorry, I find this a bit broad. Can you
it's
maybe
very broad. So my first, well, when I see the system, I think of a very specific outside the education context. Sure, use it when you want to configure a small simulation or teach about linked lists and so on, or some kind of smaller problems. And I'm having a hard time to find the transition to scale this thing up.
Yes. And
I'm ending up with, oh, at some point I want to use my keyboard and be more productive, less drag and drop, whatever. But this could be a fallacy, I know. So like, this is what we learned about, and so this is what we try to go there. So, what are your strategies to not fall into this fallacy?
So there's a lot of unknowns here. We don't know yet. But something that we observe very often, this is remarkable, I think, is that when we show this to people who have less technical skills, that are trying to build software but have never taken like any computer programming courses, are just trying to scrape things together with using ChatGPT or like Excel or like low-code environments. When they see our tool, they see possibilities that experts, well, don't necessarily see. They see limitations. They think, okay, well, I could never use this to build my spaceship at my company. But I don't know. Like, I guess just the future will tell us, like, if that is ever going to be possible. But I think my point is that even if it's not, maybe there is something to it, like to this thinking that we could try to make computer programming resemble creative applications more, that this could be helpful in the end. So.
Thank you. Let's thank the speaker. We have one more question. Sorry.
Thank you. Yeah, thank you so much for the super interesting talk. So one line of research that I'm interested in is using kind of similar like visualization techniques to extend existing languages. Sorry. So I'm wondering, from your experience building Algot, you know, kind of designing this own standalone system to kind of allow people to visualize state, do you think that there's anything to be learned from that to apply to like existing languages for, you know, building tools for languages that people already use? And yeah, just generally, how do you feel about that whole line of research? Do you think it could be fruitful?
So I just want to be clear that building this has been a collaborative activity with my students and me. So my experience and theirs might differ. But to get back to your question, so are you asking like, sorry, I was a bit distracted. Are you asking like the difference between using this like as an add-on to existing languages or like?
Yeah, exactly.
Okay.
Yeah, generally, like, do you see promise for applying similar techniques to allow people to visualize state in existing languages? I guess especially for like professional developers. And are there any like learnings specifically that you've taken from developing this language that you think could be helpful for existing languages?
I hope so. I mean, it would be quite a lot of work, like integrating a new visual language with existing technology is a lot more difficult task than to, well, build something from the start with it, like, or like to build a tool that is intended to be used that way. Maybe that's something that we could look into the future, but like it means that the way that we represent data, like I mean, it has to, Algot is graph-based, so that's what we one limitation from the beginning, and also integrating it with existing code is also would be a challenge because the computational model is very different. I think it's useful and intuitive, but well, we don't have a lot of nesting, for example, like a way you do in a typical imperative textual programming language. The query system works differently, so it's maybe something worth exploring. It could be maybe that could be the killer application in the end. So.
Thank you so much.
Let's thank the speaker again.